All right, welcome back everyone. We're going to continue our discussion on wood, this being day number 3, and in this video what we're going to be looking at is framing and some shop fabricated woods. This corresponds to chapter 6.9, 610, 611 from the textbook if you're following along there. So let's start with the idea of framing and what we mean when we say framing. When we talk about framing, it is this frame of the building, right? The framework, and you can see some pictures down here. This is your typical framing. Provides the structural support for the building, and for residential construction at least, this is the most common. This is called stick framing, where you see all these 2x4s and some headers and some things like that, which we'll talk about in just a little bit. So getting us familiar with some of the terminology we use here. Something like a floor or floor and ceiling. Some of the components are like a sill plate, otherwise known as a bottom plate or a sole plate. And that's that member that's like right down here, that's sitting right on your foundational wall. And that's what our walls, our stud walls, will be sitting directly on, right? Then we have our girders, our beams, or principal beams. This would be our beam right about there, this outside beam, sometimes called a girder, and connected to that, moving in, what we have are individual joists, our floor joists. You can see our floor joist here connected to this exterior girder, or I shouldn't say exterior, but the outside girder. Now, terminology can get a little bit funky here because I was calling this a girder. You might also call it a header joist, meaning you have these individual joists coming in and it's the top of all of those. I don't know. I've heard both those terms used somewhat interchangeably. We also have our subflooring. So we can see our subflooring is this OSB is what it looks like that he's gluing down right now. So all of the subflooring means it's going to be below your final flooring, right? If we look at our joists are the spans of these joists can be regulated by these design codes. This is the International the International Building Code, the IBC. And if we read through this, what this says is a dead load of 20 pounds per square foot. So based on that design load, if you're using, say, 2x8 for your joist, and let's say you had Douglas fir, then you could look at your notice this was, remember this rating, this would be a number 1. Then you see that we could have a span of 12 foot 4 inches, and you can see as your species changes, that could affect your span slightly. Of course, if you go with a deeper beam, deeper means it's stronger, so a 2x12 could span 17 foot 5 inches, or if we got smaller with the 2x6, only 9 foot 8. So you can kind of see how that table would lay out based on this International Building Code. There's also a specification on this joist spans based on the National Design Specifications. This is the NDS, and it's your main wood authority. And the NDS would inform the International Building Code, so there should be some overlap there. So this is just a different table, but another view of what it might look like. And this would be based first on the modulus elasticity, E. If you remember, modulus elasticity was basically how much we're going to have for deflection down. In this case, we're saying, what if we just have 2x8s? And we said, what's our spacing between our 2x8s? Well, let's say we had 16-inch spacings between each one of these studs for our 2x8s. And then we could look at this modulus of elasticity. Say we had a 1.2 million elasticity value, then I could have a span of 11 foot 8. So just a different way to read these tables. And if you are the engineer behind it, you may actually even look at the bending stresses and what kind of values you have in PSI and calculate what load you could have. But that's, of course, beyond the scope of this class. So moving vertically, all that was horizontally, moving vertically to our wall assemblies, what we have are plates, and we can have a double top plate. We see a double plate up here. We could have a plate down here. This is your sole plate. We already talked a little bit about that when we called it a sill plate or a bottom plate. And So we have top plate, bottom plate, and sill plate. Now we can also have a sill plate up here, which is the same idea. It's basically just the bottom of what you're building on, and that sill plate in essence is underneath your window or a door opening. We have our studs, which are these vertical members, and we can have different types of studs. We have our king stud. Our king stud goes the full length right next to the window or a door opening, and then right next to our king stud is our trimmer. So our trimmer would be like right there, right? Should be using different colors, I suppose, but I can see my trimmer right there framing out that space, and then my king stud goes all the way from floor to ceiling. We can have a cripple stud. The cripple studs are these tiny little studs that go from the header up to the top, or a short stud. We can have the header itself. So a header is on top of either a door opening or a window opening. And we also have our sheathing, which isn't really shown here, but that would be, of course, like our OSB or something like that, that is covering up our spanning over those studs. So here's some picture examples because pictures are always good. I can see my double top plate up here. What else do we got here? Some kind of header right here. We're supporting our header. So this would be your king stud, and this would be your trimmer. This is actually a double header, so supporting a lot of load. We're stacking two of these on top, and you can see we actually have three of those trimmers supporting it. Still have your king stud going all the way up. Corner framing, you have some kind of framing along here. What the corner framing usually is addressing is how you're going to attach your drywall or whatever else framing materials or whatever finished materials you might have, or just how you're going to tie the corner together of these two walls, right? So some things to keep in mind when you are looking at your wall assemblies is the orientation of the studs and the spacing. So spacings will be designated with this OC, meaning on center. And so typically we're talking 12 inches on center or 24 inches on center. And some of that will be based on the span that the 2x are going to make sure that they're not overloaded. Also, quality of connections. We'll talk more about connections in just a bit. Here's a rule of thumb on spacing for these residential wall assemblies. If I had a 2x4 wall and I had it 24 inches on center, 24 is a pretty large spacing. You're really only supporting the ceiling and the roof. And you have to space them closer together if you're supporting more load. So that's why we're dropping down to 16 inches on center if you're also supporting a floor above in addition to the ceiling and roof. And you need to bump it up to a 2x6 stud if you were going to have two floors. So higher the load, the closer the spacing. You may even have to increase the size of your studs. That's what that's really saying. Moving to the top and talking about the roof and ceiling assemblies, we have some components here. We have the ridge beam. The ridge beam is on the top part of your roof, right about there. As you can see, principal beam running along the roof at the peak connects all of our rafters. So of course these are our rafters. They're angle joists connecting the ceiling and ceiling beads to the beams, to the ridge beams. We also have ceiling joists, lateral loads, carrying elements, connects the girders or beams. You can't really see them, and this isn't really showing it, but they're going horizontally through here. And as you look up from that floor up, that's what you would see. And also we have this roof sheathing. Once again, it's not actually shown, but that sheathing is just your OSB or whatever structural member you have connecting all those together. And so here's a picture of the process. What we have is, we see way up here we have our ridge beam, and we have our rafters coming down from there. Another picture, good picture of the sheathing, and you can see how the sheathing is going on. Once again, strong direction is going perpendicular to those rafters. We can see that. So with these roofs, we have a number of different types. We have like a shed roof where it's at an angle, but we just have the one side to the whole thing. The gable, one of the more common ones, right? I have the hip, and the difference between a hip and a gable is this is now inset, and I have this other side to it, you know, the two sides, and then I still have the gable structure, I guess, on the top, right? A flat roof. Now, flat roof isn't totally flat. There has to be some way that it is actually draining, but it's a very, very mild slope to some way to shed off that water. Butterfly roof, you can see it's collecting all the water in that bottom part. Combination roof would be a combination of some of these others. Mansard, gambrel, you can see these. We also have different types of trusses. So trusses are based on this idea that they're made out of triangles, and what this allows is for these very large spans without using very much material. And as far as the structure itself, it's in essence like I had these pieces pinned together, like they aren't actually being bent in any kind of way. Everything is either in tension or compression, and that's what makes it such a strong thing. So they're triangles, everything's either being pulled or pushed, nothing's being bent with these trusses. And the pitch of the roof is basically, you know, your rise over run. What is the slope of your roof? And if you have a steeper roof, of course, that would shed more water and allows more room for working up in the attic area for HVAC or anything else. So different components of a truss. We have the web gusset, and this little gusset is connecting these members together. We have our ridge gusset. Anytime you see these gussets, right, basically it's a connection plate. We have our top cord up here, which is this whole member going along here. Our bottom cord coming along here. And then we have our web, and our web is these intermediate connecting those top cords and your bottom cords. And these trusses do have names. This is a Fink or W truss. I didn't really touch on the names, but you can see those as well. So like I said, there's these gussets. Now when we're connecting gussets together, we might have something like a connection plate, right? And you can see a number of ways that you can connect things together. Nails and joist hangers and so on and so forth. When we talk about nailing, one of the most common practices, there's different ways we can nail boards together. This one is called end nailing. The reason it's called end nailing is because your nail is actually going into the end of this 2x over here, right? So that's why it's called end nailing. Versus face nailing, both of these members are being connected from their face, right? So end nailing, face nailing, toe nailing is coming in at an angle, sometimes because of access or based on the loading that you're looking at. We also have blind nailing. This would be like a hardwood flooring or something where you're nailing through the tongue of each one of these members, and then when you put the groove over the tongue, it is in essence a hidden nail. So that's called blind nailing. So the nails should be loaded in shear, and remember, shear is like a force that's almost like karate chopping it through, right? So this type of force. So if I have my nail on a board, I don't want it to be loaded for pull-out. They aren't designed for that, but instead designed for the shearing force. As far as our size of nails, you'll see the little D after it, right? Like a 20D. D stands for penny, so that would be a 20 penny nail. And we have different gauges. Gauge would be related to the diameter of the nail. Of course, the bigger diameter, the stronger the nail, because what we're looking at once again is that shearing, that karate chopping. And you know, if I have a bigger, fatter material, it would take a much more force to shear through it. And then, of course, you can see the lengths based on this penny designation. There is this one little note that thicker nails, sizes 10D to 60D, are referred to as spikes, so everything over that way, right? And here you can see from the IBC, the International Building Code, some fastener requirements, and you'll see some of the same stuff. So if it's going to be toe-nailed, and the spacings and things like that. Here's another thing that we should be familiar with floor framing is this idea of bridging. What bridging is connecting these joists together. So in this case, I see this little strap, this metal strap, and what the strap's doing is it's tying them together. It's keeping them from that torsional. It's providing torsional rigidity. And sometimes what you'll see is like a block in here, right? Like a block of wood, same type of idea, just tying everything together. We can also have these shop fabricated wood structures, and these are pre-assembled at a shop and then shipped out, as opposed to just having a milled piece of lumber, right? And we can have a number of these things. We can have structural panels or pre-framed panels. We can have rigid frames, box beams, roof trusses. These are the more common ones. I see there's this insulation between the two members of OSB, so that would be some sort of structural panel would be my guess. We have these joists, wood joists, I-joists we'll talk about in just a little bit. And there's a lot of great advantages to having this type of stuff. You get greater strength, so you can have bigger spans, or you can have speedier construction because it's more of a modular construction type of process. Trusses are often pre-manufactured or shop fabricated, and they're just brought out to the site. You'll see a lot of these in the back of the truck already. You're just stacked up and ready to go. Throw up those roof trusses. We have I-joists, and we'll talk more about those in a little bit, but here's an I-joist, and then we have these floor trusses. So we talked about trusses before for roof trusses, but it's the same idea with a floor truss, but of course now we have a flat surface all the way across, but we still have a top chord, bottom chord, and these webbed connections to tie the whole thing together to give us an extra strength. And these trusses, like I said, can span further. They're much more rigid. You also have more room in here for like ductwork or plumbing or anything else if you have to go through these members. So these are our shop fabricated I-joists, and what we're getting out of these I-joists is a much greater strength, because structurally, if you were to bend something, the bottom is in tension, the top is in compression, and those are the parts that really are carrying your loads, right? The very top and very bottom. So the idea behind an I-beam, either a metal I-beam, a wood I-beam, or anything else, in this case an I-joist, is to put a lot of material on the top and the bottom for this bending part of it, right? And that's what keeps it stiff and rigid. This inner part, this web part, is for the shear of the material, meaning the material might just want to be cut in half. And so to give us our shear strength, we have the web, and to give us our bending strength, we have the top and the bottom flange. And this can be made out of different material. It could be sawn lumber, laminated veneer lumber, laminated strand lumber. And this is what I was just saying, the flanges resist the bending, and the webs resist the shear. It does say the webs can be made out of OSB, like this little example here. I see the OSB in there. And so this would be an example of how we get that greater span, right? So so if I had like a 9.5 inch deep I-joist and I had them 16 inches on center, depending on what series it is, I'm talking about spans of like 16 feet plus a few inches, right? If we compare that to a 2x8 with 16 inches on center, you know, how far can we span? Even if we have the best of the best, we're only looking at 14 foot 8 inches. So we do get a greater span out of our wood I-joists. Here's a picture of some I-joists in action. I have joist hangers connecting it at the end. I can see I have an OSB for my web section, and it looks like this is like a glue lamb type of bottom chord and top chord, where I have multiple layers glued together to create a strong structural member. So that's what I have for this presentation. I hope you found that enlightening as usual, and I'll talk to you all later. Thanks.